Hello guys, I hope you're having a good day. Welcome to other chemistry lesson. If you don't know me, I'm an Andres Prias, chemistry teacher in an international school full-time, and I am also an IB chemistry examiner with more than 30 years of experience. Today, I will teach isotopes. This is a very important topic for chemistry, not only for the IB chemistry syllabus. So if you want to know this topic completely, just stick around. Let's start it. Okay, guys, the topic in the IB syllabus is structure 1.2.2 isotopes. The structure of this video is that first I will talk about the learning objectives. I will explain the topic in detail, showing you exercises and definitions, also concepts and theories, and then we will practice in past paper questions for real exams. And at the end, I will show you even more questions for you to practice, and I will share the mark scheme if you need it, if you require it. Okay, let's do it. Structure 1.2.2, as I mentioned, this is isotopes are atoms of the same element with different number of neutrons. This is basically the definition of isotopes. You will need, in this case, to perform calculations involving non-integral relative atomic masses and abundance of isotopes from given data. So we will talk about abundance, we will talk about non-integral relative atomic masses, and of course, we will determine the relative atomic mass of an atom considering the abundance in different isotopes. Okay, so this is the learning objective. I will explain this now. Here we have that isotopes are atoms of the same element with different number of neutrons. This is very important, guys, and I will like to explain and show this element, which is carbon. We know the carbon that we know in the periodic table with the atomic mass 12.01 has 6 protons, 6 neutrons, and 6 electrons. This is the carbon atom, and if you count in the nucleus, we have the 6 protons and the 2 neutrons, and we'll have 6 electrons. But there is another one, and there is a carbon 13, and we say carbon exists. Yes, there is another version of carbon. We said carbon exists in different. The thing is that in this case, carbon 13 is the one that contains 1 neutron more. This is in nature, but the abundance is different of carbon 12. The thing is that if you check this, we have 6 protons, the same protons of carbon. If you see this and this, carbon 12 and carbon 13, they are both isotopes because they are carbon and they will share the same quantity of protons. And this is very important. The quantity of protons is not changing. Neutrons, if you see in carbon 12, we have 6 neutrons. In carbon 13, we have 7 neutrons. That's why when you add protons and neutrons in order to determine the atomic mass, you will have 12. And if you have carbon 13, you have 6 protons and 7 neutrons, and it will add 13. That's why it's carbon 13. If you see the number of electrons is exactly the same because we are not talking about electrons. Remember, the isotopes is just different number of neutrons, and for that reason also different mass. But these carbon are not the only versions of carbon. We have another carbon. We have carbon 14. What is the difference? Again, the number of neutrons. If you see protons, we have 6 as carbon 13 and carbon 12. Neutrons, we have 8 in this case, meaning that we have 2 neutrons more. If you add 6 and 8, it will be 14. That's why it's carbon 14, considering the atomic mass. And the number of electrons is still the same. These 3 version of carbon are isotopes of carbon. They exist in nature. The difference is that they will be in different abundance. So we need to consider the abundance to calculate the average atomic number or relative atomic number. So if carbon 12 exists in nature and carbon 13 exists in nature and carbon 14 exists in nature and the mass is different, the mass will be the relative mass. That is something that I will explain in a minute. So first, I will explain the abundance here in a little square, and then I will explain this formula. So let's imagine, let's say 10 students in the classroom. Let's say 5, 1, 2, 3, 4, 5 boys. And let's use in another color 1, 2, 3, 4, 5 girls. If we have 5 boys and 5 girls, the total amount of students is 10. We say that 10 is the 100% of students. The abundance is 100% of the students. But now, I need to know what is the abundance of boys and what is the abundance of girls in the classroom in terms of percentage. What will be the percentage of 10? 5 students. So 5 students will be the 50%. Yes? So we have 50% of girls, and then we will have 5 boys, meaning that we will have 50% of boys. This is the abundance, is the quantity of part in a sample. 50% is the abundance of boys and 50% is the abundance of girls. Let's do another example here. Sometimes this topic of abundance is unfamiliar for some and is complicated for another one, so this is important. We have again 10, but in this case, let's change the color, one color more representative. Let's use red. We have 1, 2, 3, 4, 5, 6, 7 girls, and we will have 1, 2, 3 boys. How many students we have in total? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 students will be 100%. But now, what is the abundance of girls in the classroom? So we just counted the number of girls in the classroom. We have 1, 2, 3, 4, 5, 6, 7. So we have 7. 7 would be 70%. What will be the abundance of boys in the classroom? We have 1, 2, and 3. This is 3 students. The abundance of students with the boys will be 30%. If you have 70 and 30 is 100, and 100 is the total quantity of students. You see? This is the abundance of boys and abundance of girls. Now, I hope that you understood what is abundance. There is a formula to determine the relative atomic mass of an atom, considering the abundance of each isotope. Here we have an example of chlorine. I will erase this. If you want to revise this, just stop and go back. Okay, guys, let's use this example. Chlorine has 2 isotopes, but remember that in periodic table is only one value for the mass of chlorine. So we need to use the mass of the isotope, multiply that times the abundance, add them, and we will have the relative atomic mass, which is the number that we will find in the periodic table. If you see chlorine 35, the mass of chlorine 35 is 35. Here we have 75.77%. So out of 100 atoms of chlorine that we capture in nature, 75.77% will be chlorine 35. Whereas we have 24.23% of chlorine 37. This is the abundance, okay? If you add the two abundances, you will get 100%. So in the formula, we have that the isotope's abundance times the isotope mass. So in that case, will be 75.77 times 35 plus the abundance of the second isotope, which is 24.73 times 37 divided by 100, which is the isotope abundance. By solving this, you can just use your calculators and you will get a number similar, if not this one, 35.48. This number is the one that you can find in the periodic table of element or something similar. So depending on the book, depending on the resource, these percentages will change a little bit, but in the periodic table, we will have a very similar value to this one, 35.48. This number will be the relative mass of chlorine. Now, your question could be, it means that all the elements in the periodic table have isotopes. Most of them will have isotopes, and all of them will have different abundances, and all of them will have this mass, okay, the relative atomic mass. After we understood what is the relative atomic mass and what is the role of the masses of every isotopes and the abundance, here we can talk about the chemical properties. So we could say that for isotopes, because it's the same atom, the chemical properties remain the same. We could say 100% of the properties are related with electrons. So because electrons are the ones that are the main character when it comes to chemical reactions, and isotopes will have the same quantity of electrons, the chemical properties will be exactly the same. But physical properties will be different. Why is different? Because some physical properties depend of the mass of the atom. And if you remember, every isotope will have a different mass. So when we talked about melting point, when we talked about boiling point, when we talked about freezing point, and all of them are related to the mass of the atom. And that's why the physical properties are being affected by different isotopes. Okay, so probably the boiling point of one heavy isotopes is different for another boiling point of the same isotope, because of the difference in the mass and the difference in neutrons. So chemical properties remain the same and physical properties are the one that will change. Okay, always when we are talking about isotopes, it comes up the topic of radioisotopes. So what is a radioisotope? I want you to see the following. Here we have two atoms. So here we have plutonium and here we have uranium. The atomic mass of plutonium 238 and uranium 234. Something happened here if you see this arrow. Okay? So if we stick to the definition of it, says that a radioisotope is the unstable form of an atom that has an unbalanced number of neutrons and protons in its nucleus, causing it to release energy in the form of radiation to become more stable. So if you see here, plutonium, which is a non-stable atom because it has 144 neutrons and 94 protons. This difference, this unbalance, is making this plutonium very unstable. In order to gain stability, plutonium is releasing energy. And when it's releasing energy, it's becoming a more stable atom, which is uranium. Uranium also has an unstable um, number of neutrons compared to the protons, but is a little bit better. We could say that is more stable. This stability is when an atom undergoes radiation or decay. If you see, for this atom to become this atom is releasing an energy, and this energy, the name of this energy is called alpha particle. This alpha particle, we have two neutrons and two protons. Is that familiar to you? We have an element which has two protons, and this is helium. Wow. In order to gain more stable, is releasing an atom of helium, meaning an alpha particle, to become uranium, which is more stable isotope. It doesn't mean that uranium is very stable, because it all the uranium will again decay and emit more energy. Could be in the way of alpha particles, or different releasing of energy in order to gain stability. Okay, so in summary, this is what a radioisotope is. In physics, the exercise are more depth, and you need to make more calculations, and you need to determine different things. But in chemistry, we are talking about radioisotopes in this general topic. So for you to know that atoms are releasing an alpha particle to get more stable. Hey guys, now this is the favorite part for some of you, because you understood the topic very well in your lesson, and now it's time to practice. This is a question taken from a past paper. This is a paper from the International Baccalaureate Organization. So, and this is a paper from paper 2. It says argon has three natural occurring isotopes: argon 36, argon 38, and argon 40, meaning that we have different isotopes, right? The mass will be different, and the number of neutrons also will be different, because they have different mass. It says identify the technique used to determine the relative proportion of isotopes of argon. The technique, we haven't talked about this because this is a topic that I will get deeper and further in a coming video. But for now, the name of spectrophotometry or mass spectroscopy. The question is the following. It says the isotopic composition of a sample of argon is 0.34% for argon 36, 0.06 for argon 38, and 99.6% for argon 40. The question is calculate the relative atomic mass of the sample, giving your answer to 2 decimal places. Okay, let's do it. So solving this exercise, remember the equation that we have the abundance times the mass of the isotope divided by the percentage, the total percentage. So here we have 0.34, which is the first isotope times 36, because it's the mass of the first isotope, plus the abundance of the second isotope, 0.06 times the mass of the second isotope, which is 38, plus the abundance of the last isotope, which is 99.6, times 40, which is the mass of the last isotope, right? Once we have the abundance times the masses of all of them, then I will divide it by 100. And this is the formula that we can use. One of the formulas. There are many formulas. For example, you can divide off the abundances by 100 and then just multiply and add them without dividing by 100. It will be the same. It's up to you. So I will do 0.34 times 36 here with my calculator, 0.0638 plus 100. And here we have divided by 100. This is 39.99. It says decimal places, 2 decimal places, 39.99 by solving this simple equation. Was very easy, right? Here we have mass spectrometry will be the technique used. Remember, this is the techniques used to determine the relative proportion of the isotopes of argon. So we will talk about this particular technique in the future. Okay, so here we have 39.99, the answer that we got. But in this case, instead of divided by 100, first they divide the abundance by 100. For example, if you see that here we have 0.34, they will have 0.0034. And then they are multiplied in time the masses, but it's exactly the same. I will stick with this formula because it's safer and you don't need to run different calculations other than this one, and you don't need to turn off your calculator again or reset your calculator again. I will stick with this formula, guys. This is what I highly recommend. This is how we solve this exercise. If you see, this is 2 marks and this is 1 mark for the technique. Okay, very easy. Okay, here we have another past paper question from the IB. This is for paper 1. It says, which quantities are different between two species represented by the notation? So remember that this notation let us know about different quantity of protons, electrons, and neutrons. Now, here we have tellurium. The question is about the number of protons, the number of electrons, and the number of neutrons. So we will calculate the electrons and neutrons for them. So remember that we have to use this very fast. I will explain step by step and how to approach this exercise easily. But remember that we need to approach this very fast. So please stop the video, try by your own, and then you will continue and solve this. You check how I'm solving this and approaching this. So we have tellurium with the information of the subatomic particles and iodine negative with the information of the subatomic particles. So let's calculate for tellurium the number of protons, electrons, and neutrons. Remember that the number of protons is here. So this is 52, is the number of protons. The number of electrons, in that case, because tellurium is a neutral atom, will have the same quantity of electrons than protons in order to be neutral. So the number of electrons will be 52 as well. And the number of neutrons will be the atomic mass minus the number of protons. In that case will be 128. minus 52. Let's do it in the calculator. 128 minus 52, and we got 76 neutrons. I will highlight them: 52 electrons and 76 neutrons for tellurium. Now, let's do the same for iodine negative: protons, electrons, and neutrons. Okay, protons, remember that is this number down here, 53. Number of electrons. This is an ion with a negative charge, meaning that we will have one more electron than protons, meaning that we have 54 electrons. And neutrons will be 128 minus 53. Let's do it anyway in the calculator to double check. Minus 53, and then we have 75. Let's highlight it with a different color: 53, 54, and 75 neutrons. Now, let's see the question. The number of protons only. Let's see, protons is changing, but also electrons and also neutrons. So this is not number of protons and electrons only. No. Number of protons and neutrons only. No, because electrons is also changing. The number of protons, neutrons, and electrons will be the correct answer for this exercise D. Okay, and this is the question. Okay, another question here for another past paper. What is the relative atomic mass of a sample of chlorine containing 70% of the chlorine 35 and 30% of the chlorine 37? Remember that we solved one exercise similar to this one before, when I was explaining the formula of determining the relative atomic mass. But in this case, we have different unknown decimal percentages here, 70 and 30. So if they are giving the abundance and they are giving the mass, it's better to calculate it instead of trusting the value that we already know. So here we have 70% times 35 plus 30 times 37 divided by 100. Let's use our calculator. So 70 times 35 plus 30 times 37 divided by 100. And here you go, 35.6. Is it option here? No. Hit option here, 35 for here. This is the answer for this exercise. Let's see the mark scheme. Yeah. Okay, now we have this exercise, also a past paper, one for a national paper. Here we have a naturally occurring gallium consists of the isotopes 71 gallium and 69 gallium. What is the approximate percentage abundance of gallium 69? I could see that this exercise is a little bit long and not challenging, but it's a little bit of algebra that one need to use. Okay, so in this exercise they are providing the relative atomic mass and they are providing the masses of the atoms. We need to determine the abundance of one of them. But if we know the abundance of one, it will be easy to determine the abundance of the other one, because will be 100 minus that abundance. Remember that always two abundances will add up to get 100. So it will be easier to calculate one to get the other. In this case, if you remember the formula, with the mass of the isotope 1, which is 71. Make this a little bit thinner here. So we have 71. We have the abundance of the other gallium, which is 69, times abundance 2 divided by 100 equals 69.72. This will be the main equation, the one that we need to solve. We need to solve A1 or A2. Now, because the relative atomic mass is closer to 79 than 71, we will say that the higher abundance of the isotope will be gallium 69. In that case, I will rearrange this equation by doing the following. So I will have that 71 times 100 minus x plus 69 times x divided by 100 equals 69.72. Okay, now what we need to do is determine x, and x will be the value that will help us to solve the exercise. Okay, so here we have, if we rearrange this, we can take this 100 up here and we can make this multiplication. So we have that 71 times 100 will be 7100 minus 71x plus 69x, because it's 69 times x. Here, let's say that we have 69.72 times 100. So this will be 6,090 Okay, now we will solve this. Negative 71x plus 69x. We have 6972. Then we have this one minus 2x. And we have 7972. Here we have 2x, and we make this subtraction here. It would be 127 minus 6972. That will be 128. So x will be 128 divided by 2. That will be 64 will be one abundance, and the other abundance will be 100 minus 64. That will be 36. One abundance will be 64 and the other abundance will be 36. Because this number 69 is closer to 69.7, we'll say that the abundance of the isotope would be close to 60. So 40 is not the answer, 50 is not the answer, 75 is not the answer. This is the closest to that number that we find out here. So that will be the answer, and this is how we solve this exercise. Okay, guys, this is the end of the past paper questions. So here we have from the book, from the Pearson one. So you can stop, try to solve by your own. If you don't know how to solve it, please write me a comment and I will be very happy to support you in this. Here we have another exercise. Feel confident by solve all of these exercises. I will post the mark scheme in the comments so you compare with the mark scheme, and then will be a safe mode. So if you watch the whole video, if you practice with the past papers and you are able to solve these exercises, it means that you are ready and you understood the isotope topic when it comes to chemistry, the IB for the cell and for the shell. Okay, so those are my two references. This is how I am taking where I'm taking the resources. So please stay tuned and don't forget to like and subscribe. Study chemistry, love chemistry. Okay, guys, have a good one. Bye bye.